I know that much, but I was going to try and mention what week we're in, and I lost track of that. So maybe we should start the countdown of the weeks, and I'm not sure what that is. Is this
we're on week 11.
4? I think we got, counting this week, this is 4 more, right? I think we got total of 4 instructional weeks and then finals week. And well, I might as well bring that up too. What I was going to bring up first is your test. And so, as you know, we've been working in 9 and 10. We wrapped up 10 last time, started some examples. That's where I want to continue today, do some more examples, because I think these 2 chapters, 9 and 10, can get pretty long here. Do we have more information coming? Yes, but not too much more. 11 is a short chapter. 12 is just as short or shorter than 11. And so these 2 chapters are going to go pretty quickly. I even mentioned it at the close of 10. I might as well say it again. This is what I'm going to say after we get done doing some examples. So I'm going to do some more examples from 10. And as I get started with 11, I'm going to say, now remember that the whole idea of chapter 10, and the reason it was so long, is we were trying to do an analogy. Everything we had done with translational motion, we did with rotational motion. And so we've learned Newton's, say, second law of rotational motion, and we've been doing some examples for that. The one exception, though, is we haven't done what? Momentum. Yeah, momentum. And you guys noticed that. And that's what we're saving for chapter 11. And that's the whole chapter. So it just continues with the analogy. And the author, like I said, decided not to keep that into chapter 10. Part of me thinks he should, but the other part of me understands. We've already had a long chapter. And the hardest analogy is momentum. So he saved that for its own little topic. Okay? But with that said, then there is no new pieces of physics until we get after the test. There is no new pieces. I mean, that new piece I just mentioned is 11, and there's no new pieces in 12. It's applications of what we've learned in chapter 12, which I think is really good, gives it time for all this new information to digest, because 2 weeks from today is the test, right? So the test on this material, 9, 10, 11, and 12 is coming quickly. And it's still 2 weeks away, so maybe it's not that quickly. Seemed like we just took a test here. But we got another one coming in. And then after that, then we just have a week and a half, and we'll do the last 2 chapters, and then we'll have finals and be done. So I'll say it again, 2 weeks. The timing as well, we'll be ready for the test. It may make 13 and 14 a little crowded as we finish up the semester. But your question was the final exam. Yes, your final exam is on Monday. That's probably not a surprise. Yes, it's in this room. That's not a surprise. What may be a surprise is what time does it start? 8 a.m. And so it starts an hour earlier than our class normally starts, or 55 minutes earlier, if that makes you feel any better. Okay, and so that want to point that out. Don't come strolling in at 8:55, 9, or some of you 9:15 to get started on the final exam. Yeah.
You know how you said we're going to do 2 more chapters after the next 10?
Or the best we can with the 2 chapters. Yeah.
How's that going to work with the final? Are we going to put...
So when it does come to the final, I'll say this: the final exam will have 1 problem from chapter 13, 1 problem from chapter 14, and then the rest of it will be spread out over the 12 chapters that we had before, which will probably be 5 problems. So a total of 7 problems. We'll do 5 from the general chapters 1 through 12, and then 1 from each of the 2 chapters we didn't kind of give its own little section. And when you see the material that comes up, it makes sense. The way it's grouped together, the first 4 chapters, the next 4 chapters, and the next 4 chapters make good grouping. And the fact that these are kind of standalone, you'll see that. All right, well, unless you guys have any kind of questions about the last, I guess, 4 or 5 weeks that we have here, you know, counting this, although you might say this is kind of the end because we already had 1 lecture in the lab, and now we have 1 more lecture. So once we're done here with 3 more weeks, and then a final exam. And of course, I'll say it again, your final exam is Monday, 8 o'clock. Maybe I should keep reminding you, 8 o'clock, 8 o'clock. Okay. But maybe I should wait till after the test, because you might show for the test at 8 o'clock. I mean, I want you to do that, okay. But the final exam is at 8 o'clock. And I don't know if this is better or not, but it's got to be your first exam for finals week. I mean, it's Monday morning, 8 o'clock. You don't have time for another one in there. So that means you'll study that one first, right? That's the one you'll spend all the time, and it's your math class that you'll go, oh, I should have studied more for that one. I spent all my time on physics, which now hopefully you'll get a good balance with it, but that'll start your finals week off. Well, we were doing some examples. It looks like we did 4, 35, 49, and that was a good one for the lab. Let me try 47 then. 47, again, is the best way I could describe all of these is, think about the description, but also think about how would you have done that if the problem was involving translational motion, and then say, okay, what will I do now with rotational motion here? And so I'll start off by just putting the number here on the board and say, okay, let's look at number 47. And again, that first step that I haven't mentioned in a while, make sure you always just get a good physical picture of what's going on here. Here it says, an object with a weight of 50 newtons is attached to the free end of a light string, which is wrapped around a reel of radius 0.25 meters and of mass 3 kilograms. The reel is a solid disc, free to rotate around a vertical plane about a horizontal axis passing through its center. The suspended object is released 6 meters above the floor. Okay, so there's a lot of description there, and then they start A, B, C, D. But pause and draw yourself a picture here and get a good idea of what's going on here. So let's see. I'll start again. An object has a weight of 50 newtons. All right, so I'll put my object here. It has a weight, and that is mg of 50 newtons. Notice they've done something a little different than they haven't done too much in the past. They gave me the weight of the object, not its mass. Could I get its mass? Sure. In fact, I'll pause and do that. I suspect I will need it. I'm not sure. But since a lot of times we do need mass, I would think that I am going to need the mass here. And I'll just go ahead and do that before I go forward here. So I'll take 50 divided by 9.8. Should be around 5. Yeah, 5.10 kilograms. All right. So there's its mass and there's its weight. The object of weight 50 newtons is attached to the free end of a light string which is wrapped around a reel of radius 0.25 meters. Okay, so there is a light string holding it. So in other words, we don't need to worry about the mass of the string. We never have been really considering the mass of the string. We never really do in this class. We obviously can't cover everything. We got to save things for later on. We obviously started with things without size and recently just gave our object size to them. So we keep expanding our ability to do more realistic problems. It does say that string then is wrapped around a reel, and so I'll just put a little circle or a disc. Later on they say that reel is a solid disc, and so there's where I'll keep going. But before I go and leave this sentence, it does say the reel has a radius of 0.25, so 25 centimeters is its radius, and has a mass of 3 kilograms. So I'll put in the little circle here 3 kilograms. I'll put a radius of 0.25 meters, and so there's my kind of my picture so far of what's going on. It says here the reel is a solid disc. Okay, I'll keep that in mind. It then says it's free to rotate in a vertical plane. Now I already drew it that way, so got lucky there, I guess. I mean, what do we mean by a vertical plane? Well, the disc is kind of drawn this way. Do I have a disc? There's my disc at the bottom here, right? And it's rotating in a vertical plane, and it says around a horizontal axis. So here's the axis sticking out. In other words, it's not this way rotating. It's not rotating around a vertical axis in a horizontal plane. It is a vertical plane on a horizontal axis. Okay, and so that's the description here. free to rotate on a vertical plane about a horizontal axis passing through its center. And that's nice to know. It passes through its center. I mean, I have a feeling there's something here about moment of inertia. And the moment of inertia is dependent on what is the shape of the object. That's why they said it is a solid real. It depends on its mass and its radius, and I need that. Okay, and it depends on what point is it rotating about. And in this case, it's its center. The suspended object is then released 6 meters above the floor. Okay, so the floor is down here, and this height then is 6 meters. Now, you can kind of see, I hope, what begins to happen before I even get to the questions. I mean, if I let this go, then that is going to be pulling, and this is going to unwind. Fair enough? So this is going to have a translational motion, and this is going to have a rotational motion. Okay, I'm assuming the axis is strong enough that it won't, you know, pull it off the wall and snap it. So there is an axis there. Okay, and now we get into the questions at hand. A, determine the tension in the string, the acceleration of the object, the speed at which the object hits the floor. Now, listening carefully to those questions, what approach would I take?
Would you do a FD or free body diagram to find the tension?
Well, I would, right? And so you're kind of answering that. What approach would I take? It would be Newton's laws of motion, right? And so remember, when they ask things like, what's the speed at the bottom, if they are asking for the speed and give you distance, which, don't they have that? What technique goes on in your mind? Conservation of energy. So yeah, I might want to do this with conservation of energy if they were only asking for speed. Now they asked for more than that. So I'm not going to do it by conservation of energy. When they start asking for what is the acceleration or what is the tension, I have to go to Newton's laws of motion. If they just ask for the speed and I have distance, then I would use energy. If they asked for speed and gave time, then I would use Newton's laws of motion. Okay, and so you got to make that decision, and it's one of the harder decisions now that we have so many different principles we can use to solve our problems. Which way are you going to approach it? In fact, let me just read B before I go forward, because now it says verify your last answer, that is the speed, by using energy principles. So really part B is going back to, hey, notice that you just did A, you got the speed, and you got it by Newton's laws, but couldn't you also get it by energy, and see if you don't come up with the same thing? And so that's the problem at hand. So A really has 3 parts. What is the tension? What is the acceleration? What is the speed as it hits the floor? Now, you guys pointed out very quickly, I just want you to see the analogy. If we go all the way back to chapter 5, if I had something that was translating, and I knew I was applying Newton's laws of motion, the first thing I would do is free body diagram. So I would do the same thing, although I would say free body diagrams, plural, because I would have one for the rotational disk. That's what's new here. And I would have another free body diagram for that vertical weight that is just descending as it goes down. And that's not new, although it's tied together with the rotational one. So of course I have to do it. And so really the reason I picked this problem was right here, was to say, look, read it, think about it, you know you're going to do Newton's laws of motion. What do? Free body diagram. See the analogy? And like I said, unfortunately, there's not enough time to do all the different possible problems you can have. And the only thing I can say, this chapter becomes easy if you see the analogy. If you go back and ask yourself, what would I have done if this was translational motion, now that I have rotational motion? And then, of course, it gets kind of hard when you realize you have both of them, and so you got 2 objects, but then you have to realize that they're coupled together. Doesn't the translational motion of this one get related to the rotational motion of that one? And so that's the connecting piece we have to put. I'll start here, free body diagram. All right, what forces are on this object? Give me one anyway. Tension. All right. That would be right here. That would be pulling down. I'll call that a T. Tension in the core. That's the first question in here. What is the tension in the core? Any other forces on this? Oh, gravity. Okay. So where's gravity here? All right, so the force of gravity is going to be at the center of mass. And maybe I should put a capital M for this one, and I'll use little m for this guy over here, okay? So capital M for the disk, and little m for this little 50, well, I wouldn't call it little, it's, you know, it's 5 kilograms here. It's not like the ones we use in lab, but it's that same idea. Any other forces here? Okay, normal force. What do you mean by normal force? Yeah, I mean, isn't there an axis here? And so wouldn't the axis be pushing up? And if you want to call that normal, maybe we should. And I don't want to. That's why I wanted to pick here. Okay? So the point is, draw your free body diagram and remember this. Everything that is in contact plus gravity. So we got gravity, everything in contact, that's the string, that's the axis. Nothing else is in contact. There it is. Those are the 3 forces that are on there. Now, I know some of you were skipping these 2. And I'm hoping you weren't skipping them because you didn't think they were there. I hope you were skipping them because if I asked you, how much do these 2 forces contribute to the rotation? How much torque do you get from these guys? None. Why not? Right. So remember, when we go to calculate torque, we said torque is the force, it is the angle between them, and it is the distance away. Then the distance away is the distance from where it rotates to where the force is acting. And in the case of these 2 forces, what is that distance? 0, right? It's rotating about its center. Its center of mass is at its center. The distance is 0. Same thing with the normal force. It is 0. So, do these forces exist? Absolutely. But do they contribute to a torque? Do they contribute to a rotation of the object? No, and that's what I want to make sure you see. Because we need to make sure we look at the forces which have to do with translational motion, as well as the torque that is provided from those forces which have to do with the rotation. So, truth be told, we could have got away with this without even thinking about these, except if I didn't put them here, you would have said, well, isn't the net force down and wouldn't it fall? Yes, if you didn't have an axis, what would happen? It would fall. It would fall not only because there's a tension here, but it would fall because of the force of gravity. You have to have an axis. So, in other words, not needed for this problem, but the sum of the forces in the vertical direction is that. And if it's not falling, then that has to come out to be 0. And so the normal force, what is pushing up is not only the weight of the object, but also then, of course, plus the tension in there. And so that would be the normal force. And then, of course, that's a nice educational discussion, but really not needed for this problem. Because when we go to solve Newton's law, here was the idea. Add up all the torques and set it equal to I alpha. Okay? And then solve the equation. So those were our 4 steps. I'll run through them again, right? Good physical picture of what's going on. Free body diagram. Write out the equation, solve the equation. So when I go to write out the equation and I go to calculate the torque, what do I get? What is the equation for the torque here? Okay, tension, sine of 90 degrees. You see that? This would be the R. There's the rotational point. There's where the force is acting as it wraps around. And it is 90 degrees. Good. And I even mentioned it last time. I'll say it again. I think everything we do in Chapter 10 is 90 degrees. Quickly change, but good place to get started. So I'm glad you mentioned it, and I'm glad you see it's 90 degrees. But it won't stay that way. But first chapter it will. We don't want to throw too much at you. You'll feel overwhelmed.
Back to the normal force and the force of gravity.
Oh.
If you were rotating an object not about the center, like the center of mass, with the normal force, it would contribute to the...
I'll draw it over here. You're saying, what if I took this reel and I put the axis right here? So it's like a piece of wood and I put a nail through it. Well, then I would say the nail is providing a normal force there. So I would still say the normal force does not give me any torque.
Oh,
but force of gravity would be here, so then I would say the force of gravity gives me some torque. So the force of gravity is helping it to rotate, sure. Sure. As you probably know, even if I didn't have a string tied to it, this would rotate. Yeah. And just like if I didn't have a string tied here, this would not rotate. Yeah. Okay, so then back to this calculation. So the force is the tension in the string. The angle is 90 degrees. The distance is 0.25 meters. That's the radius of the reel. And that has to equal to I alpha. So what's I? Yeah, and we did this one, didn't we, last time? We said, what is the moment of inertia of A? And then this is why they said solid disk. So you remember, right, good. You remember it's 1/2 mr squared, where m is the mass of the disk, r is the radius of the disk. At least if it's around its center. And this one is about its center here. So this would be 1/2 times 3 kilograms times 0.25 meters squared. And then the last piece, alpha, right? The angular acceleration. So this would be writing out the equation for this first free body diagram. And basically why I picked it. So you would do exactly the same thing we did in chapter 5, except we're doing a rotational object instead of a translational. And of course the next step is to solve this equation, but you can't solve it by itself yet because you got 2 unknowns. So we have to move on to the other free body diagram.
What is the question asked? The rotational?
The first part says what is the tension in it. I think the second part says what's the acceleration. Determine the tension in the string, the acceleration of the object, and the speed at which the object hits the floor. So, which I'm not sure why the author doesn't just call that A, B, C, but and then D. But anyways, he's got 3 parts here in A. So this is what I'm after for the first part. We're never really after the angular acceleration, although hopefully you can see that there's a connection between the angular acceleration and the linear acceleration. That's what they're after, this linear acceleration. So more on that in a minute, but let's do the second object. Let's do the free body diagram here. So what forces are on this one? Okay, so the tension is pulling it up, good. Gravity is pulling it down. We were already told its weight is 50 newtons, so I'm not even going to go back to 1.5 kilograms multiplied by 9.8 only to come up with 50. So we were given the 50 newtons there. And maybe I should put the mass though as 5.1 kilograms in my free body diagram. So again, good physical picture of what's going on with that object. Yeah, free body diagram for what's going on with that object. Yeah, and then write out the equations. And again, this is chapter 5. So it's a nice review. Like I said, that's why I like this chapter. It reviews the stuff we did and then adds to it. But this one, I think you know, let's just add them up. It does beg the question about positive and negatives. Which way you want to call positive? Shall we call positive down? I'm thinking that might be a good choice, only because did you notice what we did back here? When you guys calculated the torque, didn't you give me a positive value? And nobody even asked, which way does this thing rotate? Clockwise. Now, traditionally, which way do we call a clockwise rotation? Negative. So we just chose the opposite of our convention. And I've got no problem with that. But I want to make sure, did you realize you chose a positive direction? Because if you skip that, you may realize, I didn't choose positive or negative. Yes, you did. You chose, by right here, calling this a positive angular acceleration. You are choosing clockwise to be positive. And there's nothing wrong with that. In fact, I even encourage that. But it's opposite of the convention. So don't forget you chose it. And as long as we chose it opposite here, this probably makes sense that this should go together, so that when this has a positive rotation, this has a positive movement. So positives here match with positives here, and I think that makes the problem a little bit easier. Do you have to do that? No. But you do need to pay attention to the choices you're making as you go along. And as I said, haven't said it for a while, but remember, you have that freedom of choice. What you want to choose is your coordinate system. But once chosen, it now has power over you, and you need to be consistent with that throughout the problem. And most students realize that. It's just they may not realize they made a choice. And so some of those labs we had earlier on in the semester where we were letting the computer choose positive and negative, and to see what you guys would do, were purposely set up that way to see what you would do, realizing that you would probably pick a positive opposite of the computer, and not realizing the computer picked one could get yourself into some positive and negative confusion in there. And so we had two good labs that illustrated that. And this just illustrates the same thing. So all that is to say is we did choose clockwise as positive, again, opposite of the convention, but that's fine. We'll do it. Same thing here to be consistent through. If this I'll call down positive, maybe I'll even put a little grid here and say, look, I'm going to call that the positive direction, because when I do that, that's why I will pick a positive 50 for the force on that object. It's pulling it down, and that's what I'm choosing as positive, whereas the tension then is pulling it up, which of course then we have to call it negative. And that has to equal the 5.1a. Okay? And so, like I said, translational motion only. The same thing we did back in chapter 5. So here's the new stuff, chapter 10, coupled together with the old stuff, chapter 5. Newton's laws, write it out. Newton's laws, write it out. Translational motion here, rotational motion here. Of course, though, you can see what we have now. We have tension and angular acceleration, and here we have tension and linear acceleration. So that's two equations, but three unknowns, unless these two are coupled together. And so we need that now next piece. And so you might call this then three equations, three unknowns. And we did this. How are these related? Well, follow this logic. If this has an acceleration of a, then the string has an acceleration of a. The string is tied to the edge of this reel, so the edge has an acceleration of a. And so how is the acceleration of some point on the object related to the angular acceleration of the object? Right, and so acceleration was radius times the angular acceleration, where the radius is whatever position on that object you are interested in. In my case, I am interested in the whole radius, not just part of it. This obviously would have been different had the string been wrapped around maybe some inner smaller pulley or spool that is on this reel, but that's not the case. And so this is the 0.25 meters, and so this is the alpha, and this is the A. So now we have three equations, three unknowns, and now we have a math problem, okay? And so we've got the second half of it. And again, not to belittle the mathematics that is going to be required to solve three equations, three unknowns. I'm suspecting that's not really the challenge for you guys, or at least it's not supposed to be, because you're that sophisticated in your math. The new stuff here is this right here, the physics. So here's an equation, and here's an equation. So let's do this first part. Let's solve it for t. I guess to do that, maybe I will first eliminate, say, alpha in this one. And let me simplify this. A sine of 90 degrees is 1. I can get rid of that. 0.25 on each side can cancel off. And so this is my tension equals, and I'll put the 1/2 and the 3 kilograms that I still have. The 0.25 meters, there's still one of them left over, but taking this and solving it for alpha, I get A divided by 0.25 meters, which is also very helpful because now that 0.25 will cancel with another 0.25. And so tension equals half of 3, that's 1.5 A. And so that's what I get with my first substitution by taking that equation and putting it into there. Now I need to solve this. I guess I'll solve it for tension first. So why don't I divide each side by 5.1, and so that will be A. So this becomes 1.5 times 50 minus T divided by 5.1. And so taking this math over to here, I've got T, and why don't I write it as 5.1 T equals, and 1.5 times 50, that's 75, minus 1.5 T, move this over to here, this becomes 6.6 T is 75, or T is now 75 divided by 6.6. So, like I said, a little bit of math, substitution, or any other piece of math you like, but it looks like 11.4 newtons then is what I get for the tension here. And I've answered that first part. And now once I've got the tension, I can get A either by that equation or this equation. I happen to like this one here. So acceleration then is the tension divided by 1.5. And so 11.4 divided by 1.5 comes out to be 7. Let's call it 5.8 meters per second squared then is the acceleration, which is a pretty high acceleration, I should point out. In fact, I'm sure the author picked the high acceleration for one main reason, but also a small reason. I'll start with a small reason. Is the acceleration then of this weight going down 9.8? No. Why isn't it 9.8? Yeah, I mean, why would it be 9.8? You only get 9.8 if you had cut the string and it was free fall, right? So you never thought it was going to be 9.8, right? Okay, so that doesn't bother you. But the high acceleration does tell us something because, again, I think there's a temptation by students to say the tension is equal to the weight of the object. Is that true? I mean, what's the weight of this object? 50. What did we come up with the tension? Yeah, 11.4. Not even close. So again, my warning, don't go down that road. The tension in the string is not at all equal to its weight. Now, it would have if the acceleration was 0, right? If you come back to this equation, if the acceleration had been 0, then tension and weight would have been the same thing. So there are times, certainly, that the tension is equal to the weight. But that only works here when the acceleration is 0, and no other forces. So if we have both those conditions, no other forces and an acceleration of 0, then it works. But that's kind of rare. The last part of this then is what is the velocity when it gets all the way down to the bottom. And this again is a linear motion. So I'm tempted to, go all the way back to my chapter 2 and ask this question. Is it a constant acceleration? Well, it looks like it is. I solved it, right? What'd I come up with? Yeah, 7.58, always. All right, so if it's always 7.58, we have a constant acceleration. And if it's constant acceleration, I can use this equation. And so starting from rest, ooh, did they say that? Hopefully they either implied it or something. Determine the tension in the cord, the speed of the object right before it hits the floor. An object attached to a free end, wrapped around, free to move in a suspended and released. Okay, so release 6 meters above the floor. So I'm hoping that's kind of enough to convince us that, okay, the author's trying to say we're going to release it from rest and to get a speed of 0. So this is 2. The acceleration is 7.58 meters per second squared, and it's going to go 6 meters. So again, getting out our calculator and putting those together, 2 times 7.58, excuse me, times 6, and the square root of all that good stuff is about a 9.54. So 9.54 meters per second is the speed as I use Newton's laws of motion.
Is there another way to solve that velocity?
Yeah, and then there's another way to solve it, which is B. B says, okay, can you also solve this one? See if I gave myself enough room here. But it says, could you also figure out the speed using energy? And yes, that was the whole point of the discussion on energy, that yeah, you can. You can avoid the tension and the acceleration. So if you don't need to know those, or aren't interested in those, and you just want to know the speed, use energy to get it. And so it's why I picked this problem. It was one that hopefully will come up with the same thing. I think I'm going to need more room. So I'm going to leave this speed on the board here. And come over here. I don't think I will need any of the free body diagram stuff anymore, and the tension and all that stuff. Let's just do some conservation of energy. Now, remember, with conservation of energy, though, we want to be real clear on defining our system. And we've really got 2 approaches here for our system. Maybe I'll take 2 different colors. One option here is we could look at just this object. And another one, of course, we can look at the 2 together. And I think it will be more instructive and educational if we look at the 2 together. And so that's what I want to do. If we look at just this one by itself, then to calculate the energies, we've got to look at the forces of gravity. That's not so hard. We've done that in the past. But we also have to look at the force from the tension of it. And that's what I'm trying to avoid, and say, look, you don't have to go through Newton's laws of motion to get tension if you do this. If you take the 2 objects together, then you have a tension here, but you have an equal and opposite tension here. They cancel off, and we never have to pay attention to any tension in the problem. And so we never have to worry of solving for the tension. That would be the good side. Unless the question was asking for the tension, then it would be a bad thing because we can't find the tension here. All right? But if we are just asking for the speed at the bottom, I would put these 2 together and realize that you don't even have to worry about what the tension is, whether it's a big number or small number. Who cares? They're equal and opposite within the system itself. You just have to look at the other things involved. And so what are the other things involved here? Well, here's where B is, where I'd say, okay, let's say that the beginning energy equals to the ending energy. And of course, then we've got to add up all of our energies that we talked about. And remember, we have 2 objects. So, fair enough that I don't need to worry about any springs, okay? I'm not going to put a 1/2 kx squared in here. That doesn't show up. But I'll start off with, say, just asking the kinetic energy. They said it starts from rest. So if these things start from rest, you're going to have no kinetic energy. The only thing to begin with is what? What energies do we have? Yeah, the gravitational potential energy, which always brings up the question, where do you want to define your 0 spot? Where do you want to call y equals 0 in calculating your gravitational potential energy? To the ground? Okay, fair enough. And if you do that, then this object is 6, right? So this would come out to be mg times 6. Now again, they gave us something a little bit different. They didn't give us m individually, they gave us m and g. So m and g together come out to be the 50. So there's my mg, there's my 50. What about this one? What do you want to do with this one? It's the same discussion we really had on the test.
Doesn't change.
Yeah, it doesn't change its height. If you want to write it out, fine, it'll cancel it off. Just don't ignore it, right? And so either realize A, it cancels off, and don't worry about paying attention to it. Or redefine a y equals 0 for the second object being somewhere else. There's no reason we can't have a different coordinate system for the different object. Or maybe the best thing to see it is just to say, you know, we really don't know how high this is, but if we just call this some unknown value y, then over here we're going to get an mgy. But when we finish the problem, how high is that object after it starts to unwind? It's still the same height y, and that's why I was saying during the test is, you know, you have to think about it, you have to include it. You may not know the exact number. Don't use that as an excuse to do nothing with it. Take that as an opportunity to write it down, and hopefully you'll either figure out what y is along the way, or it'll cancel off, and in this case it will cancel off. So bottom line is, the only thing we really need to be concerned with, and all of the energy really comes from the gravitational potential energy of this weight. This weight is going to be moving down and lose 300 joules of energy, and so where does it go? Alright, so now imagine this thing coming down to here, and right before it hits the ground, and I say right before it hits the ground, I'm not going to include any heat, so we're going to ignore the fact that there might be some air resistance. We're going to ignore the fact that there might be some friction with the bearings as this thing unrolls here, but no heat energy. This thing loses 300 joules, and where does it go? Kinetic energy. How do I calculate kinetic energy? 1/2 mv squared, right? And am I done? No. And this is the new piece for this chapter. What else goes here? 1/2 I omega squared, right? They're both moving. One is translational motion, so it is a translational kinetic energy. The other one is now spinning or rotating, so it has a rotational kinetic energy. And so there is the crutch of the problem in B. Where does that 300 joules of energy go? Some of it goes to translational motion of the little hanging weight. Some of it goes to the spinning disk.
Does omega velocity have the same relation with like...
Right, and now in order to solve this, I got to realize that, hey, these two are coupled together. The translational velocity of this one is related to the rotational velocity of that one. And so just like we were able to make the connection to their angular and linear accelerations, there's got to be a connection between their angular and linear speeds here. And so let's go through that same logic. That same logic is, okay, if this is moving down with a speed v, that means the string is moving with a speed v, which means the place where the string is tied, which happens to be the rim, would be moving with a speed v. And so if you look at points on the rim and say that they are moving with a speed of v, how are they related to the angular speed of that spinning disk? Times r. And so that was our mathematical relationship between the linear speed on the disk and the angular speed on the disk. And of course in this case we got to also connect the linear speed on the disk with the string, and the string back to the weight. So once we get that, we can then use this to connect those two. And in this case, we're trying to solve for v, so let me get rid of the omega. So this is 300 joules equals 1/2, 5.1 kilograms is the mass of this weight that's hanging, as we solved earlier. And then the 1/2, and then the I is 1/2 times 3 times 0.25 squared, and then the omega is v over r. Right? And so there's how I would substitute in my numbers. And so in place of the omega, I put the v over r. And what's nice about that is I put in everything I know, and the only thing I don't know is v, so I should be able to now solve the math here for v. So I'll put a 300 here. Half of 5 is 2.5 v squared. This came out pretty nice. The 0.25 squared on top and the 0.25 down below cancels off. So this becomes 3/4 0.3 v squared. And so what do you get? You add a 5 and a 5 make a 1. And that's, whoops, 5 and a 7. Not a 5 and a 5. A 5 and a 7 make a 12 and then carry over. All right. Yeah. Oh, and yeah, and then the v squared. So when I put the two together. And now I can solve for v. And so 300 divided by 3.25, square root of all of that, and 9.6. What'd I get over here? 9.5. So 9.6 meters per second, the speed. And other than maybe some rounding, I got the same number over there. Okay, and so there's the speed at the bottom. So a little bit of a long problem, a lot of parts to it, but I thought was pretty enlightening. Let's try another one here. Did I miss something? No? Yeah, all right. I see a lot of you looking and pointing. And usually when that happens, it means I messed up and skipped something, wrote something down wrong.
You could use this and then you plug in the velocity of acceleration and then find the acceleration to find the tension if you...
Sure,
I mean, it would be
yeah.
a little bit longer way to put it. Come up with the roundness.
Yeah, I don't even know if it would be longer, it may even be shorter. But yes, that would be a very clever way of saying, hey, I'm going to come up with the tension by using the back door. In fact, maybe I'll put that diagram on the board here. Remember, we had this. We had position, velocity, acceleration, net force. Maybe now I'll just put sum of forces. And as we got started, I said this was chapters 1 through 4. This was chapters 5 and 6. Then we jumped into the idea of energy. And energy said we could get speed, but by taking the backwards approach from the energy, we could get force. And so what you're really saying is, could I get to force? Sure. Energy leaded to speed, leaded to acceleration, leaded to force, as opposed to just, you know, the free body diagram and writing it out. So, yeah, that's what, you know, you're saying and all that. All right, well, 71's a good one. It really is kind of the same thing. In fact, that probably could be said about all the problems. Once they begin to all look the same to you, hopefully you're like, okay, this is just the same problem, different situation. Obviously, then, when you see that, you're ready for the test. You're ready to say, all right, give me any configuration, and all I got to do is write it out, get the equation, and then solve the equation, right? But you know, that physics part, writing out all the equations, is the hard stuff. But hopefully you're seeing what we're after, which is this very simple principles, right? And you know, I guess good time to do it again. Physics is about knowing how to apply a few powerful fundamental concepts to explain a universe of phenomenon. And so the idea is you just start with that concept, conservation of energy or conservation of momentum, and write out the equation and solve it. 71 is kind of like that, although it does show you something that is new for the first time. We have the tension is not the same all the way throughout the string or the rope or the cord or the cable, whatever you want to call this. Look at this one here. 71 says 2 blocks are shown in figure 71 that are connected by a string of negligible mass that pass over a pulley of radius 0.25 meters and has a moment of inertia of I. Okay, so the picture is probably a good place for me to start. It's got an incline and kind of a little drop off here. On the incline is a 15 kilogram object of mass M1. And up here near the top of the pulley, or the top of the incline, the string is tied around a pulley where we now hang a 20 kilogram object, which we'll go ahead and call mass 2. And they say that what's going to happen, doesn't surprise you, is that it's going to accelerate up the hill. And they give us a number of 2 meters per second. Each second. At least that's in the picture. I haven't read that far yet in the problem. All they said is it wraps around a pulley that has moment of inertia I. Okay?
Would that be a disk?
I don't know if it's a disk or not. I haven't got that far. In fact, it won't even tell me, unfortunately. So I'll never know. Keep reading here. 2 blocks are shown in figure 71. Got it. They are connected by a string. Got it. Strings of negligible mass. Got it. Over a pulley. Radius 0.25. So maybe I will put radius 0.25 meters here. Okay, so there's my radius. Don't know if it's a solid disk yet. Turns out I'll never know. It does have a moment of inertia of I. So they don't tell me that. The block is on a frictionless incline. Okay, so there's no friction to worry about. It's moving up with a constant acceleration of 2 meters per second each second. So that's what was in the diagram there. That makes sense. A, determine the tensions T1 and T2 that are part of the same string that wraps over the pulley. So not included in my picture yet is they call this T1 and they call this T2. It's all the same string. And here's the warning I wanted to give you. Up until this point, haven't we always said the tension in the string is the same? And why did we say that? Massless, frictionless objects, and then that's how it worked out to be the same tension. You can't have the same tension anymore now that you give your pulley mass. Why not? I mean, let's do the free body diagram for that disc up there on the, or I don't know if it's a disc, the pulley. It's some kind of wheel up there. But in this picture, I would have pulling this way T2, right? And pulling this way, I would have T1. Any other forces here? Gravity and normal force, right? There's going to be an axis here. And so there's an mg and there's a normal. And so good, you saw it from the last time that, you know, I always debate if I should include that. I never want to forget that those forces are there, but how much torque do they contribute? None. And so if I'm talking about something rotating, I don't really even need to think about those there. But I'll kind of make them a little small. But when I go to add up all the torques, don't I have 2 torques coming from the T1 and T2? Can you see that they're making the wheel rotate in different directions? So before we get too far, which way you want to call positive? Down, the wheel's rolling or spinning.
Wave acceleration.
All right, but I think what you meant by down is when this one goes down, let's call that positive. Which means when this one goes up, let's call that positive. Which means when this one rotates clockwise, let's call that positive. All right, so which one is giving it a positive rotation and which one is giving it a negative rotation? T2 is giving it a positive rotation. T1 is giving it a negative. Now let me ask you this. Or maybe I should keep going with the math. All right, so let's do T2. So how much torque do I get? And maybe I'll just write it this way. Torque number 2 added together to torque number 1. How do I calculate torque from number 2? Okay, tension 2. Sine of 90, good. Times what? Okay, times the radius, which they've labeled here as 0.25, but let me just call it R for now. Okay. And it's a positive one, right? What about the other tension? Okay, good. I heard someone say negative. What else? T1, right? Sine of? Now, does this help? They said that the incline in the picture was 37 degrees. Oh. So does that help?
Yes.
So, if it helps, you're seeing the wrong thing. It's irrelevant. It's 90 degrees. And one of many reasons I picked that. Why 90 degrees? Yeah, what does this phi in the equation, I'll put it over here, torque, mean? What does F sine phi R mean? What are you talking about when you say phi? The angle between what? Yeah, from the direction the force is pulling and the lever arm, or the distance, which in this case is the radius of it. So in this little picture, this would be the R, this would be the angle. And that angle still 90 degrees? I don't care if the incline's at 37 degrees. That's going to be important here, but it's not important here. Okay? And one of many reasons I picked this one. It's a good one to see. It's not just the angle of the slope, it's the angle of what? Okay, and there's different angles going on here. So this is the angle between what we say the F and the R. What is the angle between the F and the R? And here it's 90 degrees. Same reason it was 90 here, it's the same reason it's 90 here. And then as somebody else said that, hey, it would still be the same R because it's, tied to the rim here of this pulley, which we don't know if it's a solid disc or not. Okay? And that has to equal what? I alpha. And so if we simplify this equation a little bit, notice it becomes T2 minus T1 times R equals I alpha. Now, up until this point, we have said T1 equals T2. How do we get away with that? Why do we get away with it? What were we saying on this side of the equation? The mass was 0. If the mass of that pulley is 0, then of course you're setting the right-hand side equal to 0, which makes the tension the same. So, until we got to this point, we always said, take a string, wrap it around a pulley. And if that pulley is massless and frictionless and the string is massless, you're going to get the same tension. Okay, we've changed that a little bit. Is our string still massless? Yes, we're not going to change that. We'll wait for further semesters for that. But we have now changed this. Our pulley can have mass. And once you have mass, you can't have the same tension anymore. And that's the consequence of that. And I hope you caught that. And again, it's one of many reasons, but a big one of why I picked this. I wanted you to see a problem where I'm going to do exactly what we've been doing for all the way through for these first 9 chapters, and all of a sudden, I say the tensions aren't the same anymore. And I didn't want you to get blindsided by that, because I want to go back to say, why were we saying the tensions were the same? What has changed? This is what has changed. Our pulleys now have mass. Okay? Our string does not. That too will require the tensions to be different. But like I said, we won't do that this semester. Okay, but we will do this semester as give our pulleys mass. And so you see it here. So don't fall under that disillusionment anymore that the tensions are the same. They can't be the same. You need to have the tension in T2 slightly more than T1 so you will get a net torque to make it rotate in the clockwise direction. Fair enough? All right. So if you see that, then this is what this equation comes out to be. Well, back to setting up this problem. I didn't mean to get bogged too much down into that, but that's why I wanted you to see in the diagram the author labels it as T1 and T2. That's why in the question A it says determine T1 and T2, the tensions in the two parts of the string. Same string, different tensions as it goes around the pulley. All right, then we do this free body diagram, which I guess we already have. So I'll keep going with this equation and fill in the pieces that I do know, but now that I've hopefully convinced you why in the past we said T1 was equal to T2, and now moving forward we're saying they're not equal to T1 and T2. And so this is my unknown T1, this is my other unknown T2. But I do know the radius of it. The radius of it is 0.25 meters. That was given in the problem. I don't know. And I can't look it up or do a calculation because they don't tell me. Is this a solid disc or is this more like a bike tire that has spokes? I don't know. So I can just leave this as an I. I don't know what that is. Okay, and then I'll put this as an alpha. And so looking closely at this, I have four unknowns really. I don't know alpha, I don't know I don't know T1, and I don't know T2. I suspect then I'm going to have four equations and four unknowns. But that doesn't surprise me. How many objects do I have? Well, there's three. That's going to give me three equations right there. And then the fourth one is going to be, how does the linear acceleration here relate to the rotational acceleration, which then also relates to the linear? And that's going to be my fourth equation. So, four equations, four unknowns. I'm thinking this is perfect, right? And so here's the equation number one. So, let's keep going here and write out the equation for the other objects and see what that gives me. I'm hoping that my four equations aren't what we call coupled equations. Hopefully I'll get like one equation with one unknown in it and I can just solve for that unknown and like, all right, that's good. Let's see what happens. So let's do the free body diagram, say, of this one. Okay? And so free body diagram here would look like what? Well, I would have gravity pulling it down. There's M2G. And I would have tension number 2 pulling it up. And so if I write out this equation, and to be consistent, you've already told me that you wanted to call the clockwise positive. So let me be consistent and call the down positive. So this would be an M2G minus T equals M2A. Oh, tension 2. Oh, this is looking good. Because I know everything but T2. All right. Right? Don't I know that this is a 20 kilogram object? This is 9.8. This is minus T2. This is 20 kilograms. And this is 2. And so they were nice here by giving me the A here, and I don't have to actually solve for it. Could have, right? 4 equations are coming out of this, 4 unknowns. But we'll save the harder one for the test and the final exam. Good, I wanted to see if anybody was listening. All right, so we can solve this now for T2. So if I grab my calculator here, I've got 20 times 9.8 minus 20 times 2, coming up with 156 newtons. So there is T2 in my free body diagram. And the other object which is 15 kilograms. When I draw that free body diagram, I would have gravity pulling it down, M1G. I've got tension number 1 pulling it up the hill. And I also have a normal force pushing sideways to the hill. So let's see, I've got the cord touching it, I've got the incline touching it, so I've got gravity, I guess I've done everything, right? And so there are my 3 forces. And if I call up the hill the positive x direction, I would have T1 pulling it up minus, so what's pulling it down? Yeah, and there's that 37 degrees again. So it is M1G sine of 37 degrees equals M1A. So good, I like this free body diagram because, again, they have given me straight up all the numbers except for T1. So T1 then becomes M1A minus M1G sine of 37. And so this is 15 times 2 minus 15 times 9.8 times sine of 37 degrees. Oh, did I? Oh, thank you. Yes, I move it to that side. It becomes a plus. That becomes a plus. Yes. Right. And that makes sense. Yeah, it's got to be the tension enough to overcome gravity plus a little bit more to accelerate it up the hill. So this is the part from gravity to balance it. This is the part that accelerates it up the hill. So 15 times 2 plus 15 times 9.8 times sine of 37. Well, sine of 37, isn't that the 3, 4, 5 right triangle? So it must be 3 over 5. Well, anyways, sine 37. And so this must be 118 newtons for T1. And that's really what part A was about. So I didn't really even need to do so far the free body diagram for this one, but I did want to do it first because I wanted you to realize why they're saying T1 and T2 are not equal, even though before this chapter we've always said that. Plus, the whole gist of the problem is about rotation. This stuff has nothing to do with the new information. So this is just a good review of chapter 5, but it's really this that is the new lesson. Yeah. Eventually. The first part of the question says find T1 and T2, if I remember right. A, determine T1 and T2, the tensions in the 2 parts. And then B, there it is, find the moment of inertia over the pulley. Right. And so to get part B, we do got to draw the free body diagram. We do got to solve for I. And so maybe continuing with the math that was here over to here, I would have T2, which is 156, minus T1, which is 118, times the radius of the pulley, 0.25, has to equal to I alpha. And this brings us to our last piece. How do you get alpha? Okay, so let's go through this again, right? We already argued that both of these would have the same acceleration of 2. But again, acceleration of 2 means the string has an acceleration of 2. The string is tied to the rim, so assuming the string moves without slipping, the rim has an acceleration of 2. And so if we know a part on the wheel that has an acceleration, we can get its angular acceleration. So its angular acceleration is the A divided by that point on the wheel, or the pulley, which in this case is also the rim. And this is a 2. So I becomes 156 minus 118.25. And I guess we'd square that when we bring it over and divide it by 2. And so after a little bit of calculator work, I get 156 minus 118 times 0.25 squared divided by 2. And I get a moment of inertia of about 1.19. And my units are kilogram meters squared. If everything worked out right, let's check our units. Here would be newtons for the force. This would be meters squared from that distance and that distance. This would be then divided by a meter per second squared. As you go to simplify this, a newton is a kilogram meter per second squared. And so as we cancel off a meter per second squared, we get left with a kilogram meter per second. So again, do the units work? Yes, the units work. If our logic is sound, our units will work out just right. So I wanted to ask if you remember the units for moment of inertia, because that is definitely new this chapter also. So.
Could you find out now if it's solid or the type of...
Do we know the mass of it?
No.
No, I still don't think we can find out if it's solid or anything, because we have I equals to mr squared for a hoop. So, you know, one that just maybe had some spokes that were thin enough that we didn't worry about it. But we got this one for a solid one. But either way, we know the I, yes, we know the R, but all that would either tell us is the mass is one value if it was more like a hoop, is another value if it's more like a disc. If it was then an annular ring, you know, like we did in the class, it's the inner radius squared plus the outer radius squared. Like, and I don't even know an inner radius, so I can't tell what object what it is. Yeah.
That'd be like a tire, or a what case that you said?
Something that looks like this. An annular ring, it is a disc with a hole in it. So it has an inner radius and an outer radius. And so, yeah.
Is then the R squared, like that, say all the mass is right on the outside, like the lowest one radius?
Yeah, yeah. Yeah, so the ring is more of a mathematical possibility, because as you I think you're pointing out, is wouldn't any object always have an inner radius and an outer radius? It would always have some thickness to it, right? So this is what we do when we say, well, the thickness really doesn't matter. And you can see that in the math. If these two are the same radius, when you add them together, you get twice as much. Divide it by 2, they cancel off, and you get that. So this is kind of a mathematical, infinitely thin ring, which doesn't really exist, but pretty close. Close enough that sometimes it's not worth making a harder calculation out of it. So these are the kind of approximations we do, but yeah. That annular ring, which I'll point again. Some of you obviously have been working on this and have been asking me about that one. Find the moment of inertia of that tire. And it's two sidewalls, and obviously it's two of those, right? You got the sidewalls, and then you got the tread. Yeah. Which you can think of it as either a ring or another annular ring, because the tread would look like this. I mean, the tread does have an inner thickness and an outer thickness. It's just not by much. And I think in the problem, they give this as 30.5 centimeters, and this is 33 centimeters, if I remember doing it. So you clearly see a 2.5 centimeter difference between them, and maybe you would be better off to think of all three of them as an annular ring. And we put those together and add the three objects together. Well, how about we do another one in terms of energy? This one's a little bit shorter. Good. We've done quite a few, and we probably need move into the next chapter some point soon here. But these are the chapters, or this is the part of the semester that I don't in any way want to rush too quickly to. It does take work. It takes a lot of work. And like I said, if you see the analogy, they tend to work better that way. But yeah, believe me, if you're not having any troubles with them, then good. Take your right hand, slap your back, do it again, and do it at each side. You know what I mean? You're getting the idea here. And, you know, don't tell anyone you did the homework in 5 hours. There'll be 5 hours on one problem, not not liking you. But I know that's going to be true for some of you. So some of you do the homework in 5 hours, some maybe 50 hours. So somewhere in between there. Okay. 72 here says the real shown in 72 has a radius of r and a moment of inertia I. Now maybe I'll pause there and turn the page. Here's the picture they have for you. They've got an incline again. And that incline is at some angle theta and has a mass of little m. And what they've done now, and the reason I picked this one, is they throw a spring into the problem here. All right, so you haven't forgotten how to work with springs, have you? And so it makes a nice review here. It's not going to be any different. We just got to put the spring and rotation together. But here's our spring, here's our object. And then there's another string tied to, or I think wrapped around. I'll keep reading here after I draw the picture. But we have this reel up here that has a radius of r and a moment of inertia I. And so that's what the picture looks like. Let me flip back to where it says a reel shown in figure 72, so there's 72, has a radius of r and a moment of inertia of I. One end of the block of mass little m is connected to a spring with spring force constant K, okay? And the other end is fastened to a second cord that is wrapped around the reel. The reel's axis and the incline are all frictionless. All right, so there's no friction on the axis and there's no friction on the incline. The reel is then wound in a counterclockwise direction so that it stretches the spring a distance d. Now, did you catch that? So you're going to come over here and take this reel and turn it. Grab it, turn it clockwise. Grab it, turn it. And when you do that, what's going to happen to this block and this spring? They're going to stretch. And so they say you stretch it up a distance d. That's when you turn it. It moves up a distance d. All right. Clockwise so that it stretches the spring a distance d from its unstretched position. Okay? And the reel is then released from rest. A. Find the angular speed of the reel when the spring has once again returned to its unstretched position. So what are we looking for? The angular speed. We're looking for speed. What are we given? Distance. What principle shall we attack this with? Energy. Conservation of energy. It's a perfect setup for it. They're asking for speed, they give us distance. Right? Had they asked for forces, I would have done Newton's laws. Had they asked for acceleration, I would have done Newton's law. Had they asked for speed after a given time, I would have done Newton's laws. But that's not what they asked. What is the speed when it returns back, which means a distance d? And so they've given me distances and they're asking for speeds. Perfect setup for conservation of energy. And of course this one involves springs, it involves gravity, it involves translational energy and rotational kinetic energy. Ah, what a great problem. Love it. All right, what could be better? And so it's got all the pieces too. Makes a good example here. And so as we apply our energy principles here, let's go ahead and look at the whole system being the spring, the pulley, and this little m mass on the incline. So I can say the same thing, that whatever energy I start with is going to be equal to whatever energy I end with. And so I'll maybe keep it a little shorter than we've done in the past. But again, what energies do we start with? Well, once we wind it up and I stop, where's the energy? Okay, good. So is there any kinetic energy? No, that's stop. Okay, so I don't have to worry about a kinetic energy of this one or kinetic energy of this one. But is there energy stored in the spring? Do we have a stretched spring? Right. How do we calculate that? 1/2 K d squared. All right. The general formula, of course, is x squared, but they have explicitly told us that you wind it up so that it moves a distance d. All right, so there's the energy stored in the spring. Anything else? Yeah, don't forget the gravitational potential energy. Now, I think you see that this one does not move up and down on the y plane, but certainly this one does. So there's going to be a change in gravitational potential energy. So again, it begs the question, where do you want to call y equal to 0?
K is
Okay, so the unstretched? Okay, so if you call y equals to 0, corresponding to when d equals to 0, then you would say that this thing is not starting at y equal to 0. You've stretched it, you've moved it up. And so it would have a gravitational potential energy of mg d sine theta. It's not d, is it? Did it go up a distance d? No, it's going up along an incline, right? And so if we draw a little triangle out of this, when this thing goes up a distance d, and this is the angle theta, it has only gone up d sine theta. All right. So that's how I would start the problem, if you will. This is what I would call its initial energy. Its energy it starts with is an energy that is stored because the spring is stretched, and an energy that's stored, if you will, because it now has height. And now you let it go. And so as you let it go, obviously this is moving back, and this is beginning to unwind. Notice, we mentioned this last time, so I didn't think we had to worry too much about it. Did I include any gravitational potential energy for the real? No, why not? Yeah, if you do, whatever you call this, which you don't know, call it unknown height y, isn't it going to be the same value over here on this side of the equation, and it's going to end up canceling off. So I've learned that lesson, and I'm not even going to mess with it. Not going to forget about it, but I'm going to realize that whatever it is, it's going to be the same on the other side. And or put another way, it doesn't change its height, so that energy, whatever it has, doesn't contribute to any of the kinetic energy it's going to gain. There's no change in gravitational potential energy. Okay, so then on the other side, what's going on when it gets back to the unstretched position? Well, it has no more elastic energy. And our definition of y equals to 0 is at that point, so it has no more gravitational potential energy. So where is this energy? Yeah, and I heard you guys say it. It's kinetic now. But it's two objects. They each have a kinetic energy. One is translating, one is rotating. So you would have two terms on there to give where did that energy go. And so there would be my equation. Also, I think what makes this problem maybe a little bit harder here is they haven't really given me any numbers. They've given me r's and thetas and phis here. And I'll read the question again. It says, find the angular speed of the wheel. Now, remember, they gave me r, m, k, and theta. So I should probably have r, m, k, theta, and they gave me I. And, yeah, the moment of inertia. Radius, r, and I. So I want to get then this v and I need to solve it. The only thing I think that needs to be added to this is, aren't these connected together? And so like we saw before, sure, that if this is moving with a velocity v, that means the string up here is moving with a velocity v, which means the rim is moving with a velocity v. And if the rim is moving with a velocity v, then the velocity v is the radius of this wheel times the angular speed of that wheel. And so it might be nice to do a substitution here and put 1/2, and in place of v put an r squared omega squared, so that I have taken v out of the equation and substitute it with an omega, which is the question. Find omega. So now if I say go through and multiply everything by 2, I get kd squared plus 2mgd sine theta equals, and when I multiply this by 2, I just get an mr squared, and here I get just an I, and each of those terms has an omega squared in it, so I'll factor that out. So 2 steps there, one multiply by 2, the other one factor out the omega squared. And now I can get the answer that they want, which is an equation for omega. This would be kd squared plus 2mgd sine theta divided by mr squared plus I, taking the square root of all of that. So divide and take the square root. So 2 more steps there, and I'm hoping I'm not doing too much math in one shot. I don't want to lose anybody because of the math, but again, that's also not the intent of what I'm trying to show you. I'm trying to show you the physics, and here's the physics of it, writing it out, and then the rest of it is solve the math, which, like I said, isn't always so easy, but there's the omega. And so there is step A, find the equation. Step B, they give you some numbers. They say, let's pretend D is, K is, and I'll skip that one because now it's just substituted in and solve it. I don't think that one's quite as enlightening as just, you know, 'cause all that, at that point it's just kind of plug and chug and give you. Well, I think you're starting to get the idea. Hopefully not boring you, and move on to other things here. But at least let's do one more here. How about number 65? It's got some more interesting properties to it that I think you will be useful to see. But it keeps illustrating the same thing. Draw the free body diagrams, or maybe I should say before that, deciding what process you're going to use. Are you going to use kinematics? Are you going to use Newton's laws of motion? Are you going to use conservation of energy? Are you going to use conservation of momentum? Obviously, so far, none of them have used conservation of momentum because we haven't seen the analogy of angular momentum with linear momentum. That's what the next chapter is about, as I was saying an hour ago. So we haven't done anything with conservation of momentum yet. That's the next chapter. Okay. So 65. Ooh, 58's pretty cool too. Yeah, maybe we'll do both. All right. But 65 here says that you have a long uniform rod of length L and of mass capital M, and it can pivot around a horizontal frictionless pin at one end. The rod is released from rest or nearly at rest, and it moves through a vertical position as shown in the figure. And so the figure looks something like this. You start off with a rod, as it says. You have a rod of length L, but it is free to pivot about its end. And so there's something stuck through the middle, maybe a bearing with some ball bearings if it's more sophisticated, or maybe it's just a piece of wood and a nail stuck in it here, okay? So a long uniform rod of length L and of mass capital M is pivoted around, and this is the important part, a horizontal frictionless pin at one end. Do you get that from the reading? Horizontal meaning this is the axis. This is the pin. The pin is horizontal, right? It's frictionless, and it's about one end of the rod. So that's what they're saying. It can pivot around its end. And so this rod might look something like this guy, and it can pivot. Obviously this one's got a lot of friction, so it's not quite the same here. But it can pivot around a horizontal, frictionless pin about its end. Okay? And so there's the fancy words in the reading here. It is released from rest or nearly at rest. So from a vertical position. I think what they're trying to say there is, we'll put it in a vertical position and let it fall. And if it was, you might argue, if it's exactly vertical, why would it fall? All right, well, try to put your pencil in a vertical position at rest. It will fall, okay? And then we can say it pretty much starts from rest. You have to get it perfectly balanced, otherwise it just falls. And so that's what they're saying. This is you're gonna try to balance it, but as soon as you let it go, it falls. So it essentially falls without giving it a push, so its initial speed is 0. That's what they're kind of after in here, okay? Almost from rest in a vertical position as shown. At the instant the rod becomes horizontal. Okay, so this thing is going to become in that position as it topples over. Okay? So at the instant the rod is horizontal, find A, its angular speed, B, the magnitude of its angular acceleration, C, the x and y components of the acceleration of the center of mass, and D, the components of the reaction force on the pivot. Well, let's start with A. A, what's the angular speed? All right, so how am I going to get the angular speed here? What principle shall I use? I would go with energy. Why? Well, they're asking for speed, and they gave me what? They gave me distance. Now, again, it's rotation, that distance being an angle. Isn't it 90 degrees? Okay, so you see the analogy? I mean, they didn't say it dropped 3 meters, but they did say it rotated 90 degrees. Right? So they gave me position. I'm looking for speed. Those were the key words to decide which way I'm going to do this. So as far as getting the speed, I would do this. I would say, okay, initial energy is equal to final energy. What would be the initial energy? And there's no kinetic, right? There's no springs. Where does the initial energy come from? Gravitational. Gravitational potential, right? mgh or mgy initial.
Is it the same density throughout?
And I'll even ask. Oh, good question. Is it same density? Let's see what he says. He wants us, yeah, the beginning part, a long uniform rod.
So then we can make our center of mass at the center of the
So it's uniform. So where's the center of mass? Yeah. So here is the center of mass. So what's the height? L over 2. So there's where it starts at. Oh, maybe I should backtrack. Where do you want to call height equal to 0? Okay, it's the horizontal position. Okay, so if we call the horizontal position, which I just took as an assumption, but if you call the horizontal position 0, then this does start off at a height of L over 2. So there's the height of it. So that's how much energy it has. Where does it go? Okay, so it doesn't have any more gravitational potential energy when it gets to the horizontal position. It goes to a rotational kinetic energy. And then there's the omega. That's how we can solve it, right? So let's put in our numbers, and maybe I should have put a capital M at the beginning because they made it clear they're going to call that a capital M. But I don't have another M there, so maybe that's not too confusing. Here's the G, here's the L over 2, here's the 1/2. Let's go to the I. What's the I?
1/3.
Is it 1/12? ML squared? Good. 1/12 is when it rotated around its center. Is this rotating around its center? So we're not going to use the 1/12. How are we going to get it? Parallel axis theorem. Wasn't that what the parallel axis theorem was all about? And that's why I thought this would make a good problem. I mean, it had the energy in it, yeah, but we've done many with energy so far. But we really haven't done that parallel axis theorem except for in lab there. And so in the class, we said if you had a rod rotating around its center, the rotational inertia of a rod about its center turned out to be 1/12 ml squared. But what I'm going to do is move that rotational point to another axis that is farther away, and that's where that parallel axis theorem came into play. It said if you know it around its center and you're going to move away from the center by a distance d, this would be the new rotational inertia of that object.
Is that 1/2 or 1/12?
Thank you, 1/12, yeah. 1/12. So the rod about its center is the 1/12. So when I put this at its center, 1/12 ml squared, and then I move how far? L over 2, I get 1/12 ml squared plus 1/4 ml squared, which of course is a common denominator of 12, and it's a 1 plus 3 ml squared, which is 4 over 12, which reduces to 1/3 ml squared. So the rotational inertia is 1/3 ml squared omega squared for this particular puzzle. Okay, and so don't forget about moment of inertia. And don't forget that the numbers we have are usually around its center, and your author does a good job of listing the table and then shifting it over. Although I think he lists this one in the table too. This is the only one that he lists that is not at its center, which kind of messes up his pattern. So I kind of think maybe he shouldn't even do that one in that table and say, look, this is the table listed at its center. Anything off of center, use the parallel axis theorem. And so this is off of the center. So now if we go to start to solve some of this, a few things cancel, and we get 3 times g divided by L square root is equal to omega. And so there is the angular speed. Now I can't remember if they gave us any numbers or we're just going to have to leave it in symbols. Yeah, they didn't give us any numbers there. So this is the speed as it gets, or its angular speed as it gets to that horizontal position. Once we know that, then B says, can you find the magnitude of the angular acceleration? Then maybe I should go back. It's part of the sentence. At the instant the rod is horizontal, what is the magnitude of the angular acceleration? Well, again, what principle am I going to use? They're asking for acceleration. Am I going to use energy? No. What am I going to use here? Yeah, Newton's laws of motion here. And that says the sum of all the torques equal I alpha. And that's what they're asking me to find here, is what is the angular acceleration when it's in the horizontal position. And so maybe I should draw the free body diagram, since I am doing Newton's laws of motion, and I should probably draw it when it's in the horizontal position. What forces are on the rod here in the horizontal position?
Gravity.
Force of gravity, okay, which you already said was halfway at its, or in the middle, because it's a uniform rod. Any other forces on it? Yeah, where the pin is, right? I mean, this pin is obviously in contact with it. And in fact, it's the only thing in contact with touching it, so the only other force is gravity and this pin. And which way is the force from this pin? Well, let's see. if it was only that way, then this would say that there is a net vertical force and the object is falling. That's not happening. So I guess it wouldn't be just that. But I want to put this, because isn't this thing going in a circle? And don't you have to have a force pushing towards the center of the circle? So this is the center of the circle. But again, if you think about this whole object, its center of mass is right here. Wouldn't you have to have a force towards the center of the circle? And that's what this is. This is a force, you know, towards the center of the circle. So really, it probably has what you might call some amount of force in the vertical direction and some amount in the x direction. Its total is something like this, and the answer is I don't know what direction it is. But I do know it has a horizontal component and a vertical component. Okay? And so I'm just going to label it as that way. Okay? And so unfortunately, you know, it's one of these things of, I don't know. But don't ignore it. Don't just say, oh, forget the vertical one. I don't know it, not important. Not going to put it in the picture. No, it's true, I don't know it. And hopefully something will come out of this before I'm done, and maybe I can figure out what direction it is. But at this point, I don't know. I just know it's some combination of horizontal and vertical and off at some angle, and I'm just hoping I can figure that out before it's all done. Okay, and that's what I wanted to illustrate, that and anything else here. But B says find the magnitude of the angular acceleration. And for just that, I don't even really need to know these component forces, because when I go to add up all the torques, how much torque do you get from these force components? 0. So when I say figure out the torque, what's the only thing you need to know about? So the torque is what? mg sine 90 degrees. They were nice, this chapter, because it's in a horizontal. If this was not horizontal, would it be 90 degrees? No. But this is that distance out, r. This is the force of gravity. When it's in the horizontal position, it's 90 degrees. If it was not at a horizontal position, it would not be 90 degrees. But I told you, they wouldn't do that to you this chapter. They'll wait until next chapter before they do that. And there's your warning. Yeah.
What happened to the normal force if it's on the ground? Is it not on the ground?
It's not on the ground.
Oh, okay.
No, it's, you know, like this thing sticking out of the wall. It's like this. So, you know, like that. And so it fell. Right now it's here. A moment later it's going to be like that. It's probably going to swing all the way around and do this. Yeah. So it keeps doing that forever. And with friction, it'll do that. Right. So, but they haven't asked us to analyze it that far. They've just said when it gets to this point here. All right. And so the 90 degrees shows up. What's the R? Yeah, half the length of the rod. Good. What's the moment of inertia of the rod? Please don't make me do it again. Didn't we do it here? It's 1/12 of its center, but we shifted it off center with the parallel axis theorem, so we've got the 1/3. So it is 1/3 ml squared, and so there's my alpha. And so I can solve this one for the angular acceleration. So the m's cancel off, the sine of 90 is 1, one of the l's cancel off here. And on this side of the equation, I still have g over 2. Bring the 3 to the other side. Divide by the L and write it a little nicer. This is 3 over 2L times a g over L. So there would be the angular acceleration here. Okay. C. Part C, no, lost track of what problem we're on, 65, okay. 65 says, C, what are the x and y components of the acceleration of the center of mass? So this is the angular acceleration, right? Meaning what? Maybe I'll just add to this, draw the picture again. Isn't this point now having an acceleration downward, a translational acceleration, but isn't it also making a turn, so doesn't it have then a radial acceleration? So that's why they said, what are the x and y components of the acceleration of the center of mass? And maybe I'll do the translational one first, because the translational one thinking I made a mathematical error, but I don't see it. So maybe everything's good. But I keep thinking that came out to be 2/3 one time before. So, but 1/3? No, seems right. Okay, but still bothered by it. But okay, I'll go to the problem here. The translational would be the radial position, if you will, times its angular acceleration. And so again, if you take a look at this, what would the r be in this step? Yeah, so here is the L over 2. Here's the distance away. What is then the angular acceleration? 3 over 2 g over L. The L's cancel off, and you end up with 3/4 of g for the tangential acceleration, or in this case you might call it the y component of the acceleration. And I really wanted to make sure you saw this. Did you notice it didn't come out to be g? It'd be g if it was just free falling, right? Without a pivot. So we don't expect it to come out to g, do we? So we would never assume that oh, it's just falling and the acceleration of the center of mass is g. That way too much oversimplifies the problem. I wish it was that easy and it could be simplified that way. It's not the way nature works here. And the reason it comes out to be this little less than g is, isn't there a force pushing up? See, if there was no force pushing up, if I did not have an upward component here, then the only force down would be gravity. And then it would have an acceleration of 9.8. But that's not what is happening. This little pivot point does push up, and that does give it an acceleration to be less than g, and that's what we're seeing here. And so we get a tangential acceleration of 3/4 g. What about the radial acceleration? Well, we learned it in chapter 4 as v squared over r, and then we simplified it a little bit to incorporate rotations as we got into this chapter, so we called it r omega squared. So in this case, the r, as you mentioned, is L over 2. The omega is over here, so that's 3g over L. And of course, that would have been square root, but I'm squaring it. So if you feel better, I'll put a square root and I will square it. How's that? All right, so that I don't lose you. But there is the omega squared. And so this is an L over 2, 3G over L. L's cancel off, and it is 1.5 G's. And so the acceleration is...
1.5?
Isn't there a 3 in there?
3.5 G?
Yeah, 3.5 is 1.5, right?
Oh, yeah.
Sorry, I should have called it 3.5. All right, so if you like 3.5 or 1.5 G's, I'll go either one, whatever you feel better with, all right? All right.
But isn't it over R and R is L over 2, so it should be times 2 over L? Is that it?
Say that again. I think I got the L over 2 right here. There's the R, L over 2.
Oh.
And that canceled with... No, it didn't cancel, right? The L's canceled.
No,
Okay. All right. And 1.5 G's. And this one might be a little surprising. If this was an amusement ride at Disneyland, Magic Mountain, you know, and you've got this rod up here and you put the little participant in the chamber right there, as they fall, right here, they would be being pushed this way with 1.5 times their weight, you know. And they would also be pushing down here this way with or have an acceleration of less than their weight. So they you know, would have a much smaller normal force contact with the floor. They'd feel very light at this point. They wouldn't feel completely weightless because you'd have to be falling with an acceleration of G for that. Which is not part of the problem, but how far would you have to go out before the acceleration is G? And now I'm just making a long problem longer. But this is kind of interesting here. Like I said, it's not part of the problem. We answered C, what are the components of it? But I think a fun one is to say, where would you be here to be free falling? So if this was an amusement park ride, you would be here, and by the time you got here, as far as up and down, you would be free falling. You know, you'd be pushed this way really hard. So assuming you were up against a wall, you would be like, you know, plastered against the wall at 1.5 times your weight, which I guess isn't that much. You guys been on the spin out one? I think you're 3 times your weight on that one. And you're like, oh, stuck to the wall and your cheeks are pulling back. Trying to until you get tired, and then you break your watch. You know, that one's got a lot of G-forces on it, much more than 1.5. But this would be, like I said, an interesting ride. And you've seen them probably at the fair. They got those big ones that go, you know, back and forth. But this is kind of an interesting one. Let me just answer that. Because we said the tangential acceleration is r over alpha. And we did the alpha earlier on. The alpha here was r equals 3 over 2 GL. And my question is, when does it exactly equal G? And of course, the G cancels off, and you end up with 2/3 L is equal to R. So a ride like this, if you will, a rod like this, out at its end point is where you get an acceleration equal to G. So if you take a rod and you hold it out here and you place an object 2/3, so I'll take my meter stick, so 2/3 is about right here. If I were to let it go, since these two aren't connected together, this point of the rod would drop away at G. And this would fall at G. So they'd be right in contact with no force between them. If it was over here, this would want to fall faster. So anything over here would stay in contact with the rod. So halfway in the rod, if I let it go, didn't it look like it was always in contact with the rod as it went down? But what would happen out here? Yeah, this point of the rod will fall away at a value faster than G and move away from the falling object, which is only G. So this is kind of a magical transition point, if you will. If you were to load this up with a bunch of quarters and let it go, 2/3 of the rod, the quarters would still be in contact with the rod. These would then fall away with a different value of G. A falling tree, or when they implode some old buildings, you'll often see that as the building or the chimneys fall, then they'll snap at that 2/3 mark, and it goes, and so there's the break point between the thing just regularly free falling. Because in other words, to remain on contact with this, you have to then be pushing it, and there's got to be stresses between them. And if this is old cement, there's a good chance that as it falls, that cement's weak, and then the rest of it falls away and breaks the cement, and then that falls with it. Oh, well, that was all free. There's a lot of interesting things here, and then this is one of them. But that was C. I think there's more parts to this. There's a part D and a part E too also. So let's go to D here. But what number are we on? 65, I think? 65. So D, finally, oh, there is no E, good. D is the components of the reaction force at the pivot. So finally, we get to what we started with in B. Here are some forces, and I could solve for them, and now I'm being asked to solve for these forces. And so let's come back to that free body diagram here. And so here is my free body diagram, and I will put, say, Fy this way and Fx that way. I will put then mg that way, and there is my free body diagram. There are all the forces on this object, okay? And then if I write them out in terms of translational motion. Now, why translational motion? What is the clue in this step that would make me think that I should study the translational, the forces, not the torques? All right? How much torques did I get from these guys? None. Notice they didn't show up. I didn't need them. That was, you might say, the advantage is that I didn't even care about them. I didn't need to know about them. I didn't have to solve for them to get all the rotational stuff because they gave me 0 torque. Now, that's fine as long as I'm not trying to solve for them. But now all of a sudden I want to solve for them. So the answer is, don't do the torques, don't do the rotation. They drop off. They give you 0 torques. They're useless. So that was my clue that I need to look at the translational. So when I come over to here and I say, let's add up all the forces in the x direction, let's add up all the forces in the y direction, I'll go ahead and do that. And again, they gave us the easy case, so that it was horizontal. You can see why now they gave us the horizontal, and you'll see why they stopped doing that in the next chapters here. But if I'm at the horizontal position, well, my force is only Fx, right? As I look at this, I got that force, and that force. You might argue that this is really one force, and these are the components of that one force. Okay, but the component of that one force is in the x direction, and that's all you have. And what does it have to equal? Is the object moving? Really? Not moving. Isn't it moving in a circle? And don't lose that. That's our chapter 6. Like I said, makes a nice review as we do all these problems. We got to look at our translational and our rotation. And so this object, as it gets right here, is in the process. The center of mass is in the process of moving in a circle. And the center of the circle is in the x direction. So add up all the forces in the x direction and set it equal to mv squared over r. How about the y direction? Let's add up all the forces in the y direction. Well, there's the 2 forces in the y direction, and what's happening there? Is the center of mass accelerating in that direction? Yes, it is. We did that earlier somewhere. we found out that it does have an acceleration in the y direction. And so this would have to be m times the translational acceleration. And maybe I'll solve this second one. It looks a little bit easier to me. I could put Fy here. This is mg. I can then come over here and say, well, what is this acceleration? It was 3/4 of g. So here is 3/4 of g. And so my force... Oh, I better watch my sign. Isn't that negative? Oh, and thank you. So I'm missing two things there. Let me just try that again. All right, so I need the mass. I need the 3/4 of g, and the acceleration is downward. And if I write it this way, that is down. And so when I solve then this for Fy, it becomes an mg minus 3/4 mg, which of course is 1/4 mg. And so there is the y component. It does have a force in the y direction. And it makes sense that it's going to be not too much, but does have to be upward, does have to be some number. Because if we didn't have an upward force, what would have been the acceleration on the center of mass? G, and we have something less than g. So we need it pushing up. And not too much, but enough to give it a smaller acceleration, and then 9.8. And it does. It reduces a little bit, so it's just a little bit of upward force. And then likewise over here then, the x component would be its mass. Its radius, as we've done many times before, is the L/2. That's where the center of mass is going in a circle. So there's my L/2. The speed v, I hope I haven't erased it. I think I did. I think I just did, actually. Wasn't it over here? Oh, I guess I can pick it out of here. This was omega. So it should be r times omega. So there's r, there's omega, and I can square that. So as I simplify some of these things, there's an m. That L/2 would cancel with one of the L/2, so I'll just put an L/2. Then it's a 3/g L. Looks like the L's cancel off, and it looks like I get 3/2 mg. Well, there's an L squared over 4, but there's also an L squared down over here. So there's L squared. Think of it as L/2 squared. But I have an L/2 here. So get rid of one of the L/2s down there and only write one of them on the top. Yeah. So I think I got that. Yeah. Oh, yeah. That probably would have been better. Yeah. I mass, and there's the radial acceleration. And it should have been the... Wait.
No, because we have the
So... But the radial, does that come out to be the same thing? Oh, I'm looking at the wrong one. That's why. Okay, yes. I kept looking at that one and going, uh-oh. But yes, your logic is sound, and then I was bothered by the numbers. But I was looking at the wrong one. But yes, so it does come out to be the same thing. And that would certainly be shorter. Yeah. And probably a better way to go. I just forgot I had done that. We had done so many other things. I started all over again. All right, well, I guess we're out of time. We didn't really start chapter 11, but we'll do that on Monday here.